Okay, so let's take a look at what's happening here. You have a wrench, so it's just a tool, accidentally dropped from the top of the mast on a sailboat. So you have this sailboat, just to simplify things. So you have this mast, okay, and you have this object, and it's dropped from a sailboat. The question is, will the wrench hit at the same place on the deck, whether the sailboat is at rest or if the sailboat is moving with a constant velocity? So here's the question, right? You're in a boat. Pretend this classroom is a boat, okay? And you take a pencil or anything, and when you drop it, here's my hand, right? So go ahead, can you guys imagine? Because when you visualize things, when you put yourself in this situation, it makes more sense. So if you take your pencil and you put it right there and you drop it, where will my pen go? Directly below it, right? Right there, right where I'm looking. Now that would be the case if the classroom's not moving, and this classroom isn't moving, is it? Let's just imagine, let's just say it's not moving, okay? But what if this classroom now is moving? What if this is moving? And then I do the exact same thing, and it's moving at a constant speed, constant velocity, not just speed, but the direction is also constant. It's not turning. Do you think that if I drop this blue pen, it will drop directly below it if this classroom is moving? What do you think? Well, let's see that. I'm gonna just make it larger here. So here is the wrench. If the sailboat is at rest, you know it's just gonna drop right here. That's easy, right? We all know that. Can you guys think that we need to test it? No, there you go. There you go. It drops directly below it. It's called free fall, right? Gravity takes things straight down. We're ignoring air resistance. It's not gonna float around, flutter around. Now let's take a look at what if this thing is moving with constant velocity, going that way. So here's the mast. First, it's attached to it. If the mast is moving this way with some velocity that's constant, and I'm the mast, I'm the pole, okay? Mast is the pole on the boat. I'm the mast, and I'm holding this object. Okay, so now the floor is moving. If the floor is moving, let's say the mast is moving at, let's even give it some speed, 10 meters per second. Slow. So it's moving at 10 meters per second. What is the speed of the object? Right now. Moving like South Park people. Kenny. Exactly, it's the same thing, right? So if I am the mast and I'm moving at 10 meters per second, this object is also moving at 10 meters per second. We call it the v of x, right? So if the velocity of the boat, the sailboat, is going to be constant at 10 meters per second, that's also going to be constant. Now, when I drop it, what's going to happen to that path of that object? Is it going to go straight down? No. It's going to curve, actually. It's actually going to go this way. But by then, let's say it dropped right here. The mast is also going to be here. You know why? Because the mast moved at 10 meters per second, and that object also moved at 10 meters per second, which is the same thing, even after I let go. No.
Because if you just drop it.
Yeah, that's what most people would have said. Now, this is what Galileo said, okay, if I have a sailboat, I have a mast, and I'm on top of that, and I drop it while the boat's going this way, where will that wrench go? So some people said it will drop behind me because the boat already moved, right? It would have curved that way and it would have dropped this way. So they tested it and they tested it. But then now the question is, you have to answer the question with another question. Here's the mast. The boat is moving at 10 meters per second. Okay?
Because constant velocity would accelerating.
The acceleration would change the situation. But this is also, if this is also going at 10 meters per second, like our picture here, right? that means then that that object is not gonna go. Question now is, what is going to cause that object to go backwards? They're both going this way. The boat is going this way. So the initial velocity, which is only on the x-axis, you guys don't want to miss out on this thing. Don't worry about that one. Don't worry about that yet. We'll worry about that yet. This is a big concept. This is what Galileo used to prove that the Earth is moving. Okay? So he goes, here's a sailboat. If the sailboat has a mast and you put an object at the top and then you drop it, if the sailboat's at rest, they said, well, it will drop right here. That's easy. No brainer, right? You just see it. You just look. It dropped right there because the floor's not moving. And then they said, well, what if you start moving that sailboat that way? Where's that thing gonna go? Some people said, well, it's gonna be left behind. It's gonna fall behind the mast because the mast already moved at 10 meters per second. What they didn't know at the time is that if I'm holding this pen and I'm moving this way, the pen is moving with me. That it's got its own vector velocity. So if I'm moving at 10 meters per second, this thing that I'm holding with me is also moving at 10 meters per second. Now here's the mind-blowing thing. When I let go, like right now, when I let go, see that? I'm actually going to use here so you can see it. Here, I'm going to walk this way. See this? I'm walking with a constant velocity. It went with me. But you notice that I dropped it right here. See that? Look at this. I'm going to drop it right by Sue. See? I dropped it where Sue was, right? But the pen landed here, right beside me. So the pen, I dropped it right here, and I was actually using Sue's head as a marker to mark, that's where I'm going to let go. The pen went and did a projectile this way. Why? Because the x, whatever speed I was walking with, was carried with this even after my hand was removed. That was a mind-blowing thing. The hand was removed right here, but the pen carried with it the x velocity that I was giving it. So people didn't believe it. Why would you, right? Why would the pen remember that that was the velocity that it was riding? But that's the way it is.
Because it's basically just like the gun problem before.
Exactly like that. That is the same situation. Yeah.
Which is much slower.
Well, what made this pen fall? Gravity. And how did gravity pull it? Down. The only force that was acting is down. It didn't affect the motion of the x-axis, right? So the mass here was going that way. So it's going in this direction. So is the object. So when you let go, the object will maintain the x velocity. Why will it maintain it? That is the question. The Vx remains constant. The big question now is again why? Why would the object maintain that x velocity? The question is, the only force that exists is in the y-axis. That is the only force. There is nothing in the x-axis that will slow it down. There is nothing there that will speed it up. So it has no choice but to continue what it was doing even after you've let go. Okay? That brings us to, if you are in a car, here's the car. Okay, here's the car, and this is you. Your car is driving at 60 kilometers per hour. Speed does not kill you, but if you have to stop, you will go through the windshield with the same speed that the car was going through. But then you go, but why? I'm not attached to the car. The car stopped. After the car stopped, I should stop too, right? But no, we don't stop because we have a physics memory of what we were doing before that change in motion occurred. Okay? That's the law of inertia. You're going to maintain what you're doing in the absence of any other force. And the only force acting here is the force on the y-axis. So it will make it fall, but it won't change anything on the x. So Galileo said, well, we'll do this on a sailboat. And then he asked the same question. So you don't see the difference whether the sailboat was at rest or moving. Well, guess what, folks? He said, the Earth is moving. and it is moving very fast. So when you do this experiment and I drop something and it lands by my feet, well, you know what? The earth is moving, just like the sailboat. So then they tested it on a sailboat that's moving faster. And yet, they dropped an object and the object fell exactly where it was dropped. But farther away, because it's faster, it's got a bigger velocity. Does that make sense?
So if you add acceleration, then it will be different.
It will be different. So now the acceleration would be, you see what happened here, if you were accelerating, so right now it's constant velocity here. See that? Did you see that? Object's here, I dropped it right here. The object fell directly underneath that. Do you see that right there? Do it again. Okay, so constant velocity. Okay, I dropped it right here and it will land right by it. So imagine you're in an airplane. If you're in an airplane and you drop a cargo, so let's say you're a Marine and you drop someone a box of food to down below, okay? United Nations does that all the time. So they drop in a war zone especially, they will drop supplies and they won't go down there because it's too dangerous. So they'll drop it from a helicopter. So here, a helicopter moving along the x-axis at a constant velocity, they drop a box. If you're looking down, where would you see the box land? Directly below you the whole time. This is what happens. When you let go, the object will start to curve, curve, drop. You dropped it right here, but it didn't land here because that X component is maintained every second. So it will land like that. It's always directly below you. So if you're driving, you're piloting this airplane or helicopter, you drop a box, you can see it below you the entire time. But if you're accelerating now, if you speed it up, then the box will be behind you. If you slow down, the box will actually be in front of you. So acceleration will change that. Make sense?
Acceleration only changes the actual things. The curve is still.
The curve will still be the same. The object will change. The acceleration, if you are the one changing the acceleration, then it will change your frame of reference. It will change your perspective. Whether the wrench is behind you or in front of you, it depends if you accelerated or decelerated. Curve remains the same. You got it. The object that was let go will remain the same curve with whatever velocity you had before you changed it. Got it? Okay, so that was a big idea, and that was a Galileo experiment there. Okay, and this one, we did this one already. Number 7. Let's do one more, and then we'll move on to more bigger things. A football quarterback throws a pass on the run and then keeps running. Okay, so imagine a football player continue to run without changing the velocity. Okay, without changing velocity. Question is, can he throw a pass? Can he throw the ball and then catch it himself? Is that possible? Yeah, if this person is running with a constant velocity that way, can he throw a football and still catch it when he's already here? How? Would he throw it like this, at an angle, or directly straight up? What would you do? You're running with a constant velocity. What? Now here it is. Let's give it a number again. The magic number 10. Just if there's a number, it's easier to conceptualize. So you're going at 10 meters per second. You're holding that football. What is the speed of that football? Still the same. That football is riding a 10 meter per second vehicle. That's your body. So I see a different answer. Think about it. Think about it for a minute. Go ahead and discuss it with your friends. How would you throw it? Turn around and make a friend. We're getting whiteboards soon. You guys are going to be drawing on tables soon. Jess, what do you think? You'd be my friend. How are you going to throw that? You're the football player. You're gonna throw it along the X, along the Y, or some angle. Keep in mind, the football is the same speed as you, right? This is a hard question. I want you to think about it. What do you think, Raniel? Turn around and talk to Sue and Carl. Let's exchange ideas. No, what's the acceleration here? What's the acceleration? 0. Okay? So, if the ball is going to be thrown, how are you going to throw it? Straight along the X? If you throw it, okay, remember, if you're not throwing the ball, you're already giving it a 10 meter per second. But if you throw it with some speed, you're going to add to the 10. Okay, think about it again. I'll give you one more minute. See all this nitty-gritty physics, right? If you throw it along the X, you're going to add to that 10 meters per second. So how are you going to throw it? Right? Raniel, tell us, how are you going to throw it? Straight up. How many of you say you should throw it straight up? Yes, you know why? You don't want to add to the X velocity. You want to match that. If you match it and you throw this ball straight up, what's going to happen is the X component, here's what's going to happen. Look at my drawing. Here is your V1 of Y. That's going to be your arm. But your body, your running, is going to give it a V1 of X. Your ball, your football, is going to go at that angle and is going to reach maximum height and is going to fall back down right here, and you'd be able to catch it. It's quite amazing. Now, if I take a basketball, see this? And if I'm moving, now I'm going to have to try to move that way at constant velocity. That means constant speed and the same direction. I'm going to try to do that, and if I throw the basketball straight up, should be able to catch it. Straight up. Should be able to catch it. You see, I walk faster that way. This made a bigger projectile. If I run now, you'll always catch it. As long as your acceleration is 0. And then volunteer to run and catch the basketball at the same time. Okay, and I said we're going to do a lab, right? Okay, so we're okay? Does that make sense? So you do not want to give another X velocity, so just the Vy is what you're giving it. Your body running is already the V1 of X. You'll travel that way. Guess what? It's going to go down with a perfect parabola, and you should be able to catch it. Right? Your speed along the X, your speed of running will determine whether it's going to be a tight parabola or a very, very loose parabola. This would be a big V of X, and this will be a slow V of X. Make sense? All right.